Okay, so we talked about the gases and the fact that we have a pressure and a volume and a temperature and a number of moles, and we've seen how to measure each one of these. So pressure, we've looked at the barometer, the idea that it can push up or pull down a column of mercury, and we can measure that height to measure the pressure. The volume we've done in the lab plenty of times. We've measured out the volumes of liquids typically, but all fluids you can kind of measure their volume by put them in a graduated vessel. The temperature, we've used thermometers, and the number of moles we'll see later we can convert between mass and moles using the molar mass in a gas law problem. And this gives us actually an opportunity to try our first gas law. So Boyle was the richest person in the world about 300 years ago. And 300 years ago, there was a lot of interest in gases because it turns out that it was commonly thought that gases cause disease. And so if you lived in areas where it was kind of smelly due to stagnant water, you had very bad air, so that is malaria. Okay, bad air in French, and of course malaria is a disease that we're somewhat familiar with, hopefully not personally, but maybe we've read about it. And it was thought originally to be caused by bad air. Of course, it's caused by little mosquitoes who live in stagnant water, which just happens to be pretty smelly. But people got really excited about the idea that gases could somehow be used to cure disease. So if you breathed in bad air, maybe you could breathe in some good air to counteract it. And so Boyle's law is our first gas law. And it was sort of a surprise to the people who discovered it that gases obey mathematical equations. And so in Boyle's law, it turns out the pressure multiplied by the volume of a gas is a constant, at least as long as your number of moles and temperature doesn't change. So as long as you're only changing one thing while looking at another thing, you have to be holding the other two things constant for these laws to apply. We'll see later on we can relax this restriction. So what does this mean? So PV equals a constant. So let's say PV equals 1, for instance. So what would that mean if we took our gas and we changed maybe the volume and we measured the pressure? And so if we made the volume 1, that would mean that the pressure would have to be 1. Okay, if we doubled our volume, and according to this law, it would mean we would have to halve our pressure. If we tripled our volume, it would mean our pressure would have to be 1/3 of what it was before. So there's actually a mathematical relationship here. And also if we went ahead and we made our volume maybe 1/4 the size before, in order to get pressure times volume equal to a constant. And if we set that constant, say, to 1, just for an example, then if our volume was 1/4, then our pressure would have to be 4 times bigger than where we started with. So gases obey laws of mathematics, which is really awesome. So if you've ever squeezed a balloon, you know that as you make the volume of the balloon really small, the pressure goes up to a point where it explodes. So we can actually go ahead and sort of draw a graph of this if you like. So if we put pressure here on the vertical axis and volume here on the horizontal axis, this looks like a curve. So we can see, over here we've got low volume and very high pressure. And as we make the volume bigger and bigger, it makes the pressure smaller and smaller. So as things expand, they tend to lower in pressure. As we compress things, they tend to increase in pressure, as long as the amount of gas and the temperature does not change. So we can set up a Boyle's law problem, and actually this is one we said earlier, PV equals a constant, and we remind ourselves, right, that number of moles and temperature must not change. And so we can write this mathematically actually as P1V1, where the ones represent sort of the initial pressure and the initial volume. Well, if we do something and we change it and we measure the pressure and the volume after, which we'll write as P2 and V2, then they should be exactly equal to each other. So this might be a nice kind of problem. So let's say we have a very nice red balloon, and this red balloon has a volume, say, of 1.2 liters. And that's when it's got a pressure, say, of, 1.6 atmospheres. Okay, I'm not quite sure why we're at such a high pressure. And then what we go ahead and we do is we take that balloon now and we lower the pressure. Maybe we let the pressure be 0.5 atmospheres. And the question is, what is the volume of this balloon? So we can probably have a rough guess here. The pressure started high and went low. So if we lower the pressure, that probably means the volume gets bigger. And sort of qualitatively, right, we can draw our final balloon kind of large, but we'd like to be able to calculate exactly what that is. So we can take Boyle's law, and this is really cool actually, and we can kind of put a check mark against everything we know. So we know the initial pressure, that is our 1.6 atmospheres. And we know our initial volume, that is our 1.2 liters. So we have everything on the left. And on the right-hand side, what do we have here? We have our 0.5 atmospheres. That's our final pressure, P2. We can check that. And our volume, that's what we're trying to calculate. So that's V2. We don't know that. So we can go ahead and put a little question mark here. And we can take this equation and we can rearrange it. So we can go ahead and just rewrite it and ask ourselves, how do we get just V2 by itself? And the answer is actually we divide both sides by P2. And we have to divide both sides by the same thing to keep the equation identical, right? We got to make sure it's still equal. So if we do one thing to one side, we have to do the same thing to the other side. And why did we divide by P2? Well, if you take P2 on the top and P2 on the bottom, it cancels out. And so we can get V2 then by just taking the initial pressure, multiplying it by the initial volume, and dividing it by the final pressure. And if we plug everything in, we have 1.6 atmospheres for our initial pressure. We have 1.2 liters for our initial volume. And our final pressure went down to 0.5 of an atmosphere. And if we keep track of units, we can see the atmospheres cancel, and we're left with liters in our answer. And if we punch that in on our calculator, we get 3.8 liters. So that balloon has really gotten pretty large, right? So we lowered the pressure, and the volume of the balloon increased and expanded tremendously. And of course, that's probably what you're doing right now. Well, probably not playing with red balloons, but you're probably breathing, at least I hope so, and you are increasing the volume of your lungs. And when you're increasing the volume of your lungs, you're dropping the pressure inside. So it's the same idea as our balloon. And what happens when the pressure inside your lungs drops? Well, air rushes in through your airways into your lungs and hopefully oxygenates your blood. Let's hope so.